Hey there, Physics 30. So we're going to go over this practice exam here that's on Quest A. So let's get at it. So a group of students here performing an experiment. You notice that they have this force time graph over here, kind of behind my timer. It's got this mass here, 0.5 kilograms. It's a kind of a triangular kind of shape. You notice the force is changing over time. So based on this graph, if the low friction laboratory cart starts from rest, so it's low friction, so we're going to know friction here, starts from rest, what's the final speed at the end of the 8 times 10 to the negative 1 seconds here? All right, so not too bad. So what we know, as soon as we see a force time graph, we jump to the conclusion that this is going to, or the area is going to end up being the impulse here. So what I'm going to do here, I'm just going to grab this image, all right? And, oh, maybe I want the units as well, because I noticed that the units are a bit off on the force and the time, so you want to make sure you take those units into account. You know, they're both times 10 to the negative 1. So because they're both times 10 to the negative 1, actually, if you forget about them, it would actually kind of work out kind of nicely. Okay, so I want to go right to the very end here, because I want to find the total impulse. So this looks like it's going pretty close to where it needs to be. And if I look down here, that's where I want to go from. I want to find this whole area, right? So remember, area equals impulse. Sorry about the color here. I'm going to just change that up here. Okay. So area is equal to impulse. So if I can find the area of this graph, then I know the impulse. And what impulse is, remember, that's change of momentum. So if change of momentum is equal to final minus initial, and remember the initial, it's at rest, right? So this is 0 because it's at rest. So really my impulse will end up being my final. Okay, that's good. And then remember, that's going to be my mass times my final velocity. So this is my impulse that I found from the graph. And then I could find my final velocity by taking my impulse and dividing it by mass. Not too bad so far. Okay, so I just need to find this area. We have the mass in the question. So you can go up here. It says here it's 0.5 kilograms. Okay, so let's find the area. All right, so they probably have a kind of a wiggle room here. It can kind of looks like that is pretty close to being a half. All right, so 0.5. I'm just going to go with that. And this is going all the way over to here. So my base here is going to be 0.5 to 8. So let's find this area out here. So the area is going to be my base times my height divided by 2, or 1/2 base times height. Okay, so 1/2 my base is going to be 8 minus 0.5. But remember, that's also all times 10 to the negative 1. So I guess I could do the math using times 10 to the negative 1, all right? So this is going to be 0.8 minus 0.05, because times 10 to the negative 1. And my height, I just had to read, because it starts at 0. If I want to put minus 0, I can. But if I look at my height here, go all the way across here, just underneath this major axis here. So 1, 2, 3, 4, 5, so that's 3.4, but times 10 to the negative 1. So this is going to be 0.34 minus 0, all right? So it's going to be newtons times seconds. So you pull out your calculator. All right, pull out your calculator here, and you get a half times. I haven't done the math yet. Sorry, this is like just on the fly. So you're doing it when I'm doing it. I get an impulse of 0.1275 Newton seconds. Okay, now what I'm going to do is I'm going to take that over here. All right, and I'm going to put that in my calculation over here, 0.1275 Newton seconds. I'm going to divide by the 0.5 kilograms. And I get my final velocity. So let's divide that by 1/2. So it really just doubles it. So 0.255 meters per second. as my final velocity. All right, so let's go back to quest A here, and hopefully they put a little bit of wiggle room in here. So what do we want? So we want this. You can see there's a little plus and minus here. Well, that's kind of ugly because they're not telling us that it's supposed to be positive or negative. But they want the AB, and then they want the plus or the minus part in there. All right. So because of this digital lab thing, we're allowed to put plus and minuses in there. So it's going to be minus to the -1 probably because it's less than that. All right. This is kind of fun because this is kind of new. Okay, so 2.6 times 10 to the -1 meters per second. So 26 -1. So let's put that in there. 26 -1. Cool. We'll see if that's right. Hope it's right. All right. Next one here. What we have here, it's hard to see. I'll put my face on this side here. So we got plutonium is discovered from dismantling atomic weapons, undergoing simultaneous alpha and gamma decay. All right? I hate the gamma decay. I don't really like that. Sensors on the outside of the container used to store the plutonium-239, that's important probably, indicate how much radioactive material is contained by monitoring the gamma rays emitted by the material. A particular container holds 80 kilograms of plutonium waste. The half-life is 24,000 years. It's quite long. All right. When the plutonium-239 decays and emits gamma photon of a very specific electron volt energy, and an alpha particle has a characteristic speed of pretty massive there, 15 million meters per second. Which of the following diagrams shows the orientation of the momentum or momenta of the alpha particle and the gamma photon that must result in the maximum impulse of the plutonium-239 nucleus? Okay, so they want the maximum impulse, which is the maximum change in momentum. So going at 90 degrees is not going to give me the maximum momentum. I think they want A here. I think they want both of those particles to be going one way so that the nucleus is shot off the other direction. So we think about, like, if they're at rest already, then the change in momentum is going to be the biggest if the two particles shoot off in this the other direction. They don't want to go in opposite directions because they're going to cancel each other out a little bit. At angles to each other, they're not going to result in the largest change. Okay, so that's my guess. Let's go with that. Okay. Oh, so I need this picture over here. So we got it says match the information. Which one is the direction of the gravity? Which is the electric force? And the force acting on the charge sphere that has the largest magnitude. The force acting on the sphere that has the largest magnitude. Do we have an option for that one? Oh, yeah, gravity, electric, and tension. All right. So let's try to figure this one out. Direction of gravity is obviously going straight down. So that's a pretty obvious one. So that's obviously going to be 6. All right. You can see here that this is getting pulled off to the side. All right. So it's going off that direction. So this little arrow here pointing off to the left. Why would it do that? Because there must be a force pushing it to the left. All right. So this must be 4. All right. But now, which of the forces is at a maximum here? All right. So what we may have to do, I'm trying to think about what it would be. It's probably the tension, because the tension is going to, if this is, let's read through it very carefully, suspended. So if it's been suspended there, then that is kind of the equilibrium force. We have these two forces, one going straight left, one going straight down. And then you have this other force that's kind of like the, maybe I can zoom in here and I'll do this and I'll describe it a little bit differently. But it's like the hypotenuse. All right, so I'm just going to look at this incomplete free body diagram here, zoom in a little bit. So what I'm talking about, actually I'm going to go a little bit more than just that. All right, oops, sorry. I want part of the bottom too. I went down here. Okay. So what I'm talking about is that we have these two forces. We're in equilibrium. So we have gravity going straight down. Here's Fg. We have the force, electric force pulling the sideways this direction. And if I were to put these forces together in kind of like a vector diagram, I can kind of see that, or they're together as an equilibrium here. I can see that this piece here, whatever this y component is, has got to be the same as Fg down here, because that's all y. And this over here has got to be the x, because this one's all x. So this is the hypotenuse, and the hypotenuse is the longest side of the triangle. So I don't have to pull, I don't have to do any math, right? I just know that's going to be the biggest force. So I'm just going to put down here the biggest force, which is tension. So number 3. All right. Well, that's kind of fun because there's 2 3s now. Yeah. Next. Oh, same diagram here. What's the magnitude of the charge on the sphere? So now what I'm going to have to do here is do a little bit of math. So let's read through this. We've got a charged sphere that has a mass suspended by an insulated thread between two vertical things, or vertical oppositely charged plates here. They're about 15 centimeters apart. And the electric field has a strength of 6,570 volts per meter is created between the plates there. The charged sphere comes to rest at an angle of 8 degrees. And the distance from the sphere from the positive plate is about 4 centimeters. That's not important here, because remember, force doesn't matter how close you are to the plates when you're between two plates, because you have a nice constant field, so the force is constant. So that information is kind of useless at this point. We're going to use the angle and the mass to determine the electric force. And if I know the electric force and I know the electric field, I could determine the charge. I don't know if you can see the formula right there. All right. So force, I can find that from the triangle that I drew previously. I know the electric field because they just give it to you, 6,570. I can rearrange that for charge. I'm good. So let's go to my picture here, because that's going to be useful. So here's my little picture. If I can find the force of gravity, I can use this triangle here, this 8 degrees here, to help me, because this is going to be the y component. I can use that to find the x component, and the x component happens to be the same as Fe. So let's find out what gravity is here. So I'm just going to pick a different color. So remember, gravity is equal to mass times gravity. And then I can just take my mass. I think they gave us the mass in the question, didn't they? Yeah, right at the very top there, 3.5 times 10 to the negative 4 times 9.81. Okay, so what I'm going to do is go back to my picture. I can write this number down. So this is just my mass times my gravity here. So 9.81. I'm assuming that we're on Earth. Always makes a good assumption. Okay, so now once we know that, I'm going to take this information. I'm going to go to this triangle. All right, so that makes this the same magnitude, just in the opposite direction. So I can put that down in that same spot. Negative 3, right? Okay, good. I kind of have a horrible 3 down there. Okay, so now I'm going to use the triangle to find x. So to find x, I got tan. I can use tan because I got the, I'm trying to find the opposite. So tan, 8 degrees. And I'm trying to find this x component, and I know my y component, my opposite. This is the opposite over adjacent. So this is my adjacent side. Sorry about the cramped space there. Didn't give myself too much space in this picture. So I'm going to take my answer that I have here, my calculator, times by tan, 8 degrees. Making sure you're in the right mode in your calculator. Hopefully by now you should be. Okay, so now we have this new force. This force, which is way smaller than the other one, because you can definitely see it from the picture, is the same thing as my Fe. Remember, Fe over Q, I don't know what I was looking at there, Fe over Q is equal to E. So if I rearrange this for Q, I don't know why I put the Q on this side. We're going to do a little swap here. So times the Q up and divide the E down. And there you go. That's how you're going to find the Q. So I'm going to take our, if I go back here, take my electric field, do the question, there you go. My electric field, that's 6,570, or 6.57 times 10 to the 3. That's my electric field, okay. So I'm going to divide by that number, 6.57 to the negative 3. Oh no, to the positive 3, sorry. Positive 3. Okay. Cool. So let's go back here. Actually, I'm done. I'll write down my answer over here so you can see what I wrote, but the answer is going to be D here. All right. So what I found here for the Q is 7.3447 times 10 to the negative 8 coulombs. So I'll go back into my question here, and I see that is answer D. Cool. Okay. Oh, there's a nice hand rule ones and stuff. Okay, I like this. Using the number directions given, which match the following to this. So we got here, what's the electric field in diagram 1? Okay, so let me just kind of snip this one too so we can analyze this here. All right. Cool. Okay, so in diagram 1, we're looking for the electric field. So what we have to remember is that the electrons come out of the negative side of this thing, and they're all going to pile up on this side, which means that the other side relative to this one is going to be a positive side. Positive. And then we know from our definition of an electric field, it's got to be coming out of the positive and into the negative, and there's a nice constant field between these. So it's going to go straight across. So this one here is going to be to the left. I'm going to keep that in mind for later. Here we want to know the electric field here. Remember what I just said, out of the positive. That's just by definition. They could have defined it elsewhere, but through P here, it's going to be down at an angle there. Okay? Now, question 2, we're talking about magnetic field. So this is where I had to use one of our hand rules. So we've got electron flow into the screen. So we're going to pull at our left hand. All right? Left hand? Yeah, okay. This is my left hand. All right? We'll pull our left hand here. We're going to put a thumb into the page. All right? So it would look, I don't know, kind of like that to you. It's going to thumb into the page there. And it's going to curl around, right? So thumb into the page is going to curl around there, okay? So what I'm going to get here, put my thumb into the page, let it curl around. That's the direction of the magnetic field. So it's going to go around in a counterclockwise motion. Yeah, counterclockwise motion. So a P, it's going to be going down through P, all right? Because on that side it's going down. Okay. On this one here, they're looking again, so we got this negative here, we got the electron flow, but we got a solenoid, so we're looking for the magnetic field. So we're going to have to determine from our hand rule where the north of the solenoid is going to be. So remember my hand rule in this one here, my fingers are going to curl around in electron way. All right, so we got to figure out how that's going to orient itself. So they're going to go around. So ignore my hand, right? Kind of put your hand so the electrons are going underneath. They're going, I don't know how I would do this, right? But they're going to go underneath, curl around over the top. So my electron flow is this way around the solenoid, right? So that's the direction my hand's going to go. And my thumb, when I do that, is pointing down. So that means, I'm using my left hand again. That means the north is on the bottom. So then if I draw my magnetic field out over the north to the south, I can see here it's going up through P. Okay, so now that I have all these pictures drawn, let's go over here and match it up to our question. So in P, my first one, it was going left, so 4, right? This one here is going down at an angle, 1, away from the positive charge, right? This one's going straight down, so 6. And this one was Let me just double check my picture. Going straight up. So that's 5. There we go. Cool. Next. Okay, so we got another diagram here. We got some wire. So like a conducting rod here, suspended conducting rod between a U-shaped magnet. Based on the slope of the graph, what's the experimental value? Oh, my straw is stuck. What's the experimental value of the magnetic field strength that the current carrying wire experiences? So there's obviously a force off to the direction of that side over there. They're using tan, and the reason they're using tan is kind of the same reason we used tan in that one of those previous questions back there with that tension one. So because they're trying to relate the two forces that are on this rod. So we have this 5-gram rod, so that's causing a gravitational force, and then we got a magnetic force off to the side there, and they're going to be related using tan, right? So I got this graph here, if I could just zoom out, right? And I got this picture. So what I'm going to do is I'm going to zoom into kind of both if I can. Maybe I can't. Yeah, it's hard to do. It's kind of a finicky little program we have here. Okay, so I'm going to draw a free body diagram of this down here beside this graph, and we're going to relate them so I can figure out the magnetic force, and then I'm going to use the magnetic force with ILB to find the B, right? That's what we're looking for. We're looking for the B in this picture. So let me zoom into this diagram of this graph here, and we're going to snip it, and then we're going to analyze it. Am I going to be able to move that side right? There we go. All right, so let's analyze this graph, and I'll make sure I give myself some space here for a free body diagram and a little bit of math. Okay, so let's zoom in here. So I am trying to figure out the slope of this graph first. So it looks like I can use the endpoints. Ooh, maybe not this endpoint, but let's find a better endpoint that we can use here. This one looks pretty good. I like that one, right? Sometimes you can't use the endpoints. I wouldn't use that endpoint. This may or may not go through 0, 0. We're just trying to find the slope. So we want our data points to be pretty far from each other, right? Pretty far from each other. And we want them to cross nicely so we can read them nicely. So I'm looking at that data point. I'm looking at this one way up here. So let me just find these X and Y components so I can find the slope really nice here. So let's go straight down. So that's 4.4 as my X, okay? 4.4 amps. Watch out for these units, right? So this times 10 to the -2, but this one's just amps. So this one here is just 2 below, so it's right there. Okay, so this is going to be 1, 2, 3, 4. This is going to be 24. So 24 times 10 to the -2 is 0.24. All right? And then down here, I'm going to do the same thing. So this is up 2, so this is at 6. All right, so that's the Y value. Let me get the X value first, actually. So 1, 2, so you can see I'm counting by like every 2 spots is 1 because there's 20 divisions here, and the same thing here. This one here, every 2 spots is going to be 1 as well, like 0.1, 0.1, 2. Oh no, 1, 2, 3, 4. Actually, this is by ones, right? Yeah, on the bottom. So this is 1.2. So 1.2 on the bottom, because that's right here. That's 1.2, and this, remember, this one is over here. It's 1.4. It's right here. Oh, my head's in the way. I can't do that one. All right, and this one here, I'm going up by 2s. Like 1, 2, 3, 4, 5, 6. Okay, so 0.06, because it's times 10 to the -2. So if I find the slope of this graph, let's do the slope calculation here. So my rise and my Y value is my final minus my initial. I'm just going to do it that way. 0.24 minus 0.06. All right. My run, I'm going to have 4.4 minus 1.2. All right. Let's see what my slope is going to be here. 0.24 minus 0.06 divided by 4.4 minus 1.2. All right? So we got a slope here. Well, at least I get a slope of 0.05625. And no units over amps. Rise over run. So this is like per amp or something. The units of that I'm not too concerned here. Okay, so now what does the slope actually mean? Okay, so the slope, if you do the calculation, this is going to be tan over current. So that's what this is. It's tan theta over current, I. And that's equal to this number. So if I see that in a calculation somewhere, or if I can rearrange for that in a calculation somewhere, get tan over I, then that's equal to that number. So let's go through the calculation of that free body diagram and see if I can find this tan over theta. All right? So let's, let me see if I can just zoom out here. I'm going to draw a free body diagram of this over here on the side. All right? So my picture looks like this. We got that rod. It's being forced sideways with this magnetic force. It's got this gravitational force pulling it down, and it's being deflected off. This is the tension here. I'm not too concerned about the tension, but it's being deflected off at this angle, theta. We don't know exactly what angle it is, and I can't just pick an angle off this graph because we don't know if it crosses through 0, 0, and it most likely doesn't. So they probably plan for that and account for that. So what I need to do is I need to kind of draw a free body diagram here that kind of relates this y component and this x component. Because remember, this y component is the same thing as my force of gravity, and this x component is the same thing as my magnetic force, because everything's got to add up to 0. All right? And they're related through tan. That's why they use tan in this graph, right? So if I were to write this out as tan, I'm going to put that on the other side over here. So I'm going to go tan theta, and I'm going to write out the math here. The math here would be the opposite, x, which is my FM, over my FG, which is my adjacent. All right? And what I could do, because I don't see the I in there yet, so tan theta, I'm going to replace these with my formulas. I got ILB here for my magnetic force, and I got force of gravity. Oh, see, now what I can do, I usually teach this a little bit differently, like make it y is equal to mx plus b, but I got this tan over I right here. This is what I'm looking for. I'm looking for tan over I, right? So if I can find tan over I, which I could just do here, just divide the I down to that side, I'll have this side equal to it. So what I'm looking for b, but because I see tan over I can replace that with this number. That's what that is. So this here, that is my slope. I'm just going to write the word slope here. Keep that in mind. So now I can rearrange this equation for b. So b, my magnetic field, I'm going to times the mg up and divide by L. So there's my calculation. I'm just going to make sure that's a G. Okay. So I'm going to take my slope, which is my calculator already, times by my mass, times by gravity, divided by the length of the wire that's inside the magnetic field. Not the whole wire. All right, you want to make sure it's inside the magnetic field. So let's go back to the question and find that information. All right. Oh, I'm zooming out. I don't want to zoom out that way. Okay, I want to zoom out this way. Okay, so we got a few things. We got the mass here. So remember what I said here in my picture. I have to go slope times mass. So my mass is going to be, let me just write that down, slope is 2.5 grams, so 0.0025 kilograms, right? Maybe you have to change that to kilograms, so you divide by 1,000. Yep. Times 9.81 newtons per kilogram. Okay, and now divide it by the length of the wire. So let's go find the length of the wire here. So I can see that the length of the wire between the poles, yep, the rod here is about 8 centimeters there. So 8 times 10 to the negative 2. So 8 times 10 to the negative 2 meters. There's already a meter, so that's nice. Okay, so times this by the mass, times by gravity, divided by 8 times 10 to the negative 2. So I get a Tesla here. So this is my B. Just the magnitude, because I don't know the direction. I probably do know. I can find the direction too. Is 0.01724-ish Teslas. So that's a good reasonable number. Remember, when it comes to Teslas, they can't be arbitrarily high. There's maximums we have, like man-made 5-ish Teslas is really strong. 1 Tesla is like a neodymium magnet. Like a really strong one, right? The ones on like fridges, they're like 0.1. So this is not as strong as it could be, but it's a good number. So what I'm going to do now, I don't know what they want as an answer. A, B, C, D, negative something. Okay, so I'm going to change this to scientific notation. 1.72 times 10 to the negative 2. So I got 1722 if I would put these in the boxes. Right? So that's what they want. They already told us it's a negative exponent, so that's a good indicator that we did something right. So 1722 is what I got. Let's go to the next page here. Magnet is dropped in the hollow tube through this one. What's a good indication of what's happening here? Okay, so what I'm going to do again, I'm going to snip this picture here because it's always good. I should be showing, sorry for saving all this work, but whatever. All right, so what's going to happen here? This is Lenz's law. So very specifically, we're going to have Lenz's law. We got this thing dropping through. We got this nice conductive material. So all the electrons in there are going to have this induced current. And that induced current is kind of like Newton's first law, or law of inertia. They don't want to move. So they're going to induce in a way to kind of push back on this dropping magnet. So this dropping magnet is coming down with the north here heading down. So the current that's going to be induced inside this is going to be in a way that they're going to produce a north on this side to force this back. All right, so there's going to be a north here. All right, so that's the first thing I'm doing. And then I'm just going to put my thumb in that direction, wrap my fingers around this solenoid. It's not really a solenoid, but let's say it is. Wrap my fingers around it, and that direction, ignore this picture because it's a picture of me, like it's kind of reversed a little bit. So it's going to wrap around and go behind this thing, right, in a way that's going to go around, and then the current is going to flip around here, that direction. Those are the way my electrons are going to flow, and they're going to do that all for the initial part. When it gets to the bottom, they're going to flip around and try to pull it back up, right, because they don't want to move. So they're going to flip around, and halfway around, they're going to have like eddies on going opposite directions to try to stop this thing. But that's what initially at this snapshot is going to look like. So I could see that that would be A. That's what this one looks like it would be. It would be A. It's going down. There's a north on the top to try to stop it. Based on my hand rule, it's going down that direction. We got another one. The principle to explain the induction induced is conservation of energy. You can't get energy from nothing, right? So you can't just produce this energy from somewhere. For this electrical energy that's being made here, so it's just got to be conservation of energy. Right. Okay, so we got this useless stuff over here. Relative to the direction of the electric, and do I need this over here? Is there stuff over here that I need? Teacher resources. No. Okay. Oh, so this is just fill in the blanks. Never mind. Okay. Zoom in here a bit so I can see it. Relative to the direction of the electromagnetic field components of EMR, they're perpendicular. That's one of Maxwell's predictions. They're perpendicular. And and they're perpendicular to the direction, the motion of the energy associated with the radiation. Everything's perpendicular here. Nothing perpendicular. That's why your hand is the way it is. You have everything perpendicular. You got the field going this way. It just has to work that way. And I know that doesn't work because this is a force picture one, but everything's going to be perpendicular here. Right? That's one of Maxwell's predictions. Perpendicular. Yeah, I'm just going to say that. I'm not going to bother reading that too much. Maybe I got it wrong because I didn't read it. Maybe I should read it. All right, so various scientists have attempted to measure the speed of light. A popular myth credits Galileo with covering and uncovering lanterns on hilltops. Rousseau used toothed wheels with more 100 teeth, and Michelson and Foucault used rotating mirrors. The experimental described the above all use the physics principle that require the nature to be uniform, not accelerated. Like as soon as they're made, they're going off the way they are. And they may be wave or particle-like. It doesn't really matter because they're going to reflect off things. So maybe that's more of a wave thing. But they could technically just like packets of energy going there and bouncing back. Actually, this is weird. I know it has to be uniform, but the wave and particle-like, so it may be wave or it may be particle. This doesn't really prove that it's a wave. It does reflect, right? The other one gets blocked by T, so it's not really reflecting, but it does have to come back. The lantern one, that could be particle, could be wave. Like I would say this could be either one. But I'd put like a star beside this one. I want to double check that one. Wave and particle. I can come back and maybe talk about that later. All right, so we got this picture here. What do we have to do here? Do we have to measure off this picture? It's got some angles here. Using green light. Okay. Do we actually have to do any math here? Zoom in here a bit. Okay, so match the numbers comparison. The index of refraction for the prism compared to the red light. Okay. So index of refraction is kind of related to like the speed, right? So as you go in, so I can see here, as the red light goes in, it slows down. And because how I know this is going to work, so if I were to draw kind of a color picture of this here, let me just draw a color picture of what this looks like. So right now this is the red light, right? That's what it says there. It says red. It's hard to read that, but it does say red. So if this is the red light, I'm just going to color code this. It's going to go along. It's going to slow down when it hits this acrylic. And when it comes back out, it's going to bend back out because it's going to have to speed back up. This line is going to be parallel to this line down here. So these two lines are going to be parallel to each other. Just mathematically, just reversing the operation. There should be no reason they'd be any different because the two sides of the top, it's a very rectangular prism. But along comes a green light. And what we know about this is that shorter wavelengths refract more. So there's going to be a bigger difference. So that means this is going to slow down more. It's going to bend in more. So this angle here is going to be less. And then when I reverse this operation, it's going to come out. And this will be parallel to this one down here. But you can see it's just a little bit offset compared to the other one. So it's spread out because of that initial bend inside the acrylic there. So this is how I'm going to answer this question. So this is going slower, right? So you can see it bent more, it's going slower, and this one's faster over here. Because this is slower, if I use this formula, which is not on our formula sheet, remember this formula, V is equal to C over N, to get this to be slower, this number has to be higher, right? If I want this to be lower, this has got to be a higher number, so I have to have a higher index of refraction. Okay, so let's see if I can use that information to do this. The index of refraction of the green prism, green light compared to the red light is higher. It's greater than, so that's 2. Okay, so that's going to be 2. The angle of green is going to be less than. You can see in my picture it's going to be less than. Right, so less than 1. The speed is going to be less than because it has to slow down more to get that extra bend. Okay, that's the only way I can really describe it. It's hard to do. Okay, so it's less than, so it's another 1. So let's put a 1 here. And the angle of refraction of the green light compared to, just a second. As they leave. The angle of refraction for the green light compared to the angle of refraction for the red light as they leave the prism, they're both the same because they come out parallel to each other. Right? You kind of, even though the angles inside are different, when they come back out, you're just reversing both their operations. If you just go through it mathematically, you're just flipping over that equation and you're just doing it again. And these two angles on the outside are just going to be the same. All right, this angle and this angle are both the same. It's coming up parallel to each other. So there we go. Cool. Particular mirror here. Let's see. Produces an upright image 3 centimeters from enlarged upright image. I'm sorry. They're moving away from the word erect. Whatever. They're not making it fun anymore. Got a particular mirror. What can we say about this? I'm sorry, I could have paused it when I did that, but whatever. Boop, ba-doo. I'm just going to snip this so I can draw all over here. I'm going to do the math on one side here. Okay, so it has a focal length. So we don't know what kind of focal length this is going to be. Is it positive or negative? But we do know the focal length of this is, for some reason I've lost the ability to write on this thing. All right, let's try this again. There we go. Let's just use green. So I know my focal length here is plus or minus. It doesn't say whether or not it's a concave mirror or not, but we're going to try to determine if it is, right? Oh, I already know. Okay, never mind. There's ways to determine this, right? Because it's enlarged, there's ways. If you just remember it, a diverging mirror will always be erect and diminished. It always gets smaller. That's just what do I mean? Convex mirror, right? Because this is enlarged, this has got to be a concave, right? Okay, that's what I'm going to say at that point right now. I'm just going to leave it plus or minus. We've got an upright image that is 3 centimeters from the mirror. So, plus also doesn't say that it's real or virtual. Okay, so let's just go with that. So my image here is 3 centimeters from the mirror. Plus or minus again. Okay, I'm going to go plus or minus. Okay. What is the distance? Is it real or is it virtual? And is it... and the distance placed, and we're looking for the object distance. Right. We're looking for DO. Oh, I did it again, didn't I? Oh, that's right. I'm still clicking on that. That's why. Okay. So we're looking for that, and we're trying to figure out if this is supposed to be plus or minus. Okay. So what we know about the object here, it's always going to be positive, right? This is always going to be a positive number, and then we might have this negative number here. So we can kind of go through and just kind of guess which one's going to be. But if I were to try to write this out, let me just go 1 over f is equal to 1 over di plus 1 over do. And I want to solve for this. I want to make sure that I get a positive number, right, for my do. If I don't get a positive number for my do, then I have the wrong combination of numbers. And we can just quickly do this. Right? So let's say I have a negative f, right? So 1 over 1, that's just negative 1, right? Now, here's where the thing is. If I have a negative 1 in that spot, right, and if I add over 1 over 3 or minus over 1 over 3, I'm never going to get a positive number. It just doesn't work, right? So my focal length cannot be negative because of that. All right, so what I can do is I can cross off the negative piece, right? The math just never works out. If I put a negative focal length in there, I'll never get a negative DO because that focal length is just so much larger. Or 1 over that number is going to be so much larger than 1 over 3. 1 minus 1 over negative 1 plus 1 over 3 is still negative. So my focal length can't be negative. So I've got to put that there, right? So I know that this has to be 1 over positive 1. If you want to put centimeters, you can. Okay. Now I've got to figure out what does my DI, is that supposed to be positive or negative? Now, what this part right here tells me is that my magnification has to be a positive number. So if I use my magnification information here, m is equal to negative do over di, negative di over do, and I solve for do, okay? Solve for do, so do is going to be negative di over m. So if I know m is positive, so this is a positive number on the bottom, then what does di have to be to make sure that do ends up being positive? Because do has to be positive. That's the definition of the object distance. It's just a positive number. Can't be negative, right? So what does that top number have to be? If I go through this, my di has to be a negative number, because a negative negative turns this positive. So that means I cross off, based on this information, I can cross off the positive one here. Okay. So now that I have all that, I can put in here negative 3. Okay. So since the di is negative, we know that this is a virtual image, right? So I can cross off these two here. Okay. Now I can go through and solve for do. So I'm going to add over, just one second, so 1 over do. I'm just going to take this and just add that over to that side there. So 1 plus 1 over 3. And then I'm going to flip that over. So this ends up being 1.333, et cetera, et cetera. Take the inverse of that, the reciprocal of that, and you get 0.75. This is a fun question. All right, so 0.75. So it's got to be C, okay? And you do the flip. I'm not going to do that in my thing here. So it's got to be, what did I say, C. Yeah, so far so good, I think. I don't know how many questions we're into here. The longest wavelength of EMR that will cause an electron to be emitted with a particular is this. So that they're kind of telling us like that's that's the longest, that's maximum. So that's like that corresponds to the minimum frequency, like our threshold frequency. If the radiation has this incident, okay, so I want to write this out because this involves one of the formulas that are not on the formula sheet, right? Let me just kind of clip this out here like that. Okay. So this involves this formula here, where I have the energy of the photon that comes in. Now the energy, remember in the photoelectric effect, goes in, it just disappears, right? It gets absorbed by one electron, and only one electron, and it's got to go into two places. It's got to go into the work function that kind of digs it out of the metal, and then the rest goes into the kinetic energy. That's what we're looking for. So to determine the energy of the photon, I'm going to go HC over lambda, and determine the work function, I'm also just going to go HC over lambda, right? So I'm going to do this, I'm not going to do this like a one calculation, but this lambda here is the lambda of the radiation, and this one over here is the lambda of that maximum wavelength, right? That's required. All right, so if I put these numbers in, I'm going to use the H, that's a 6.63 number, because I want my answers to be in joules, not electron volts. So I don't want to like round twice. I can see the numbers here. They're far enough away from each other. I probably wouldn't run into any problems if I did that, but I'm not gonna risk it. All right. So 6.63 times 10 to the negative 34. Speed of light divided by my wavelength in meters, which it already is. So I'll do the photon one first. Okay. So this one ends up being 1.32 times 10 to the negative 18 joules. And if I do it again for the other number, let's just retype the whole thing out. I could have just went back and changed one number in my calculation, but I didn't. So this is the energy that's actually required. So I only need 7.3666 repeating times 10 to the negative 19 joules. This is 10 to the negative 18. So this is enough energy to do this. So I'm bypassing, like one of these could have said, it doesn't work. I could have done that. Like it doesn't have enough energy or something. But in this case it does. And then I minus these two numbers, because I'm just going to minus this over to the other side. And that gives you the EK. This isn't too bad. So I get D. Okay. So if I minus that over, I get D here. So let's go back here. Boop. So we get D. Cool. Next. All right, another one here. We got a thorium 230. So I might have to figure out what thorium is. So I pull out my formula sheet. If I had one. I wish I had one around here. I know I do. Just 1 second. Okay, pulled my formula sheet so I have my periodic table. All right, so I can find thorium somewhere on there. Okay, that's down there at the bottom here. It's thorium is 90. So it's thorium 230. The alpha particle is emitted at a velocity of 500,000 meters per second to the east. The mass of the resulting daughter particle is blah. The daughter particle, so that's the big guy. Okay, we're just using for one. Okay, so what is the one that comes out? So what is the daughter particle? Okay, so undergoes alpha decay, and the physics principle usually determine the atomic number, which is the bottom number, that's charge. Okay, so let me just snip this. We're going to draw this out. I know they gave me a bunch of information here that I'm not going to use. Right? Maybe I'll use it in like a future question or something. But in this one, they give us masses and stuff that we probably don't really need. Okay, so thorium 230. This is thorium right here. It's going to undergo alpha decay. And remember, alpha decay is kind of a helium nucleus, right? Not too concerned about the charge here. But the bottom numbers here are going to add up, so I've got to have 88. So it's got to be Ra here. So I cross off that one. The top numbers had to add up as well, so this is going to be 226, right? If I get this right, because my head's right in the way of this picture. There it is. Okay, and 88, just to make sure, yeah, it's Ra, right? Now remember, this guy's going to be excited. He's eventually going to release a gamma particle, but I'm not too concerned about that. But to do this bottom number, those had to add up, because that's what we're talking about, the atomic number, these bottom numbers here. We're doing conservation of charge, so that's A. The top numbers are nucleons, the bottom numbers are charge. Okay, so we got all these little paths over here, bunch of particles. Do they have the same mass? And blah, blah, blah. They enter the bubble chamber. It's identical velocity, so that's important. What can we say about these particles? Okay, so let's just kind of read through this here. Do S and W have the same mass? Yeah, actually, I have no idea if they have the same mass. I know they have opposite charges, but because I don't know the actual charges, one if it has more charge than the other, but less mass than the other, maybe it would result in the same curve. Right? So we don't know if they have the same mass, but if you look at the next line down, we do know they have the same charge to mass ratio. All right, one can have bigger mass and a bigger charge, and that kind of just balances out with something that's smaller mass and smaller charge, and they just result in the same curvature because they're all going to the same identical velocity. That's all. Now, if I were to try to figure out like the mathematically, how would I know this kind of possible thing? So let's think about this mathematically. I know I'm going to go into a little too much detail in this question, but I'm just going to do this here. Okay, so mathematically, the radius is determined by a couple of different things, right? So the radius with this circular motion is determined by, let's go QVB, because this is going to be a magnetic field here. So this is going to be mass times acceleration. This is going to be QVB. Because I'm looking at radiuses here, I'm going to go V squared over R, because that's one of my constants. Okay. And then I'm going to start rearranging this. I'm just going to cross one of these V's off right now, divide both sides by that. I'm going to rearrange for R, so times that up and divide the other stuff down. So this is what R is dependent on. It's dependent on the magnetic field, which is constant for all of these. It's dependent on V, which is constant for all of these. It's also dependent on mass and charge. But I don't know if they have the same mass because it's also dependent on charge. Right? So there's both those guys could be manipulated in all of these paths. So if they have the same radius, it means the mass and the charge, or at least the ratio between the charge and the mass has to be the same, right? Like this could be doubled and this one would be doubled, and they kind of balance each other out. So 2 has to be an answer here. Let me just do that. So we don't know if they have the same mass because we don't know their charges. We do know they have the opposite charges because they're going in opposite directions. So that's definitely true as well. T and U have the same nature of charge because they're both going in the same direction. That makes sense. They do not have the same charge to mass ratio because they don't have the same radius at all. T and U have the same mass? I don't know. And V could be a neutron, yeah. This one that goes through the middle, because it's not being deflected, doesn't have a charge, so it's not producing a magnetic field. It's not going to produce a force with another magnetic field, right? Remember, moving charges will produce a magnetic field, but it has to be charged. Okay, so what do we say it was? 2, 3, 4, 7. Am I down in the box there? I can't tell. There you go. 2, 3, 4, 7. Sweet. Oh, am I done? That's it. All right, let's see how well we did. 0 questions, submit test. Oh, come on, numerical response number 3. What did they say it was? We got everything else right. Let's go back to that question there. Oh, what did I mess up on this one? What did I say it was? 4. Yeah, okay, 4 is right. I don't know what they just said it was wrong. I could have checked what the answer was. So 4 is right. Okay. I put it in the wrong order. I went 1, 3, 2, 4. I had to go 1, 2, 3, 4. Right? I put it in the wrong order. I'm pretty sure I got the numbers right. So yeah, that one's going to the left. 3 is going down to an angle. So 3 should be where the 1 is. Oh, okay. This one was going, based on my hand rule, is going down. So that's going down to 6. So I had these two middle ones. I'll poop on this thing. Let me just erase all this. So I had the two middle ones mixed up because I put them in the wrong order. I was doing the 2 electricals and 2 magnetic, but I should have went in the order of the diagrams. 1, 2, 3, 4. Sorry about that, guys. Let me put this in. Now, you got to be very careful about that. Going up, that's 5. There we go. Let's finish my test off now. Yay! There we go. That wasn't too bad. Yeah. All right, I'll see you maybe on the next field test. See you later. Bye.